let's talk about the origin of the UV visible absorption. For that, we're going to be doing, for example, here, butadiene. And for butadiene, let's remember that we have here 4 carbon atoms that are sp2 hybridized, meaning that in each of the carbon atoms, we're going to have 1 p unhybridized orbital. So from 4 atomic orbitals of type A, we're going to make 4 molecular orbitals. And this is, say, energy. This way is going to be increasing. And I'm going to draw what is those molecular orbitals. So these are just my P's. And when I build the molecular orbitals, we're going to have, say, 2 orbitals that are lower in energy, which we call the bonding MOs, and 2 higher in energy, which we call those anti-bonding MO. So molecular orbitals. So here you have 2 pi electrons, 2 pi electrons. So total we have 4. So this will be, you put 1, 2, so Aufbau principle and Paul's exclusion principle, and the other 2 electrons are here. So that's the configuration of the ground state of butadiene. So what happens when light of the particular wavelengths, say, will excite one of these electrons in the orbital that is occupied of highest highest energy. So let me reword this. So this is highest occupied molecular orbital, HMO. So highest occupied. So when the light, say, strikes on the sample, we're going to have one of those electrons in the HOMO jumping into an empty orbital. And this orbital, the next one, is called the LUMO, so lowest unoccupied molecular orbital. So now the configuration, the electronic configuration will change, and now the excited butadiene will have the following configuration. So this is energy again. Now I have these as the first orbital, phi 1, phi 2, phi 3, phi 4. This used to be the phi 2, the HOMO, and the LUMO is phi 3. But if I have the right wavelength, exactly matching this gap, I will have that excitation, and one electron will jump up. And so we will have those 2 here, and now the new electronic configuration, this is the excited state. And now we have a new HOMO, which is the orbital, highest occupied molecular orbital. And now my LUMO, this is a 4, but it's not seeing well, okay? That would be my LUMO. Now, the origin of the UV spectroscopy is precisely that light is being absorbed here in that region. And that changes, conjugated systems do that. This is a conjugated system, so they absorb into the UV visible. What changes with this wavelength, we're going to call lambda max. So the spectrum, the UV visible spectrum of butadiene would look something like this is absorption, something like that. And this, I think, is 217, the absorption of that. So this is in nanometers. And we call that lambda max. What happens with other conjugated systems is that if they are more extended, now the energy levels come closer. So I'm going to make another drawing just to compare. If we had, instead of butadiene, which is what I drew here, this is butadiene, ground state, excited state. So if I had, for example, hexatriene, well, this is 1, 2, 3, 4, 5, 6. So this is 1, 3, 5 hexatriene. Hexatriene. And this is 1, 2, 3, and 4. So 1, 3 butadiene. All right. So now what happens when I have 6? I will have 6 atomic orbitals. I'm mixing those 6p orbitals to make 6 molecular orbitals. The picture now is just that the levels are being squeezed, say, and now they're going to come closer. So I'm going to have 3 here and 3 here. These are my bonding MOs, and these are my anti-bonding. And I have here, see, 2, 4, 6 pi electrons. So in my orbitals, the pi system, I will have 2 and 4 and 6. So here, this is my HOMO. If I label this 5, 1, 5, 2, 5, 3, and then 4, 5, and 6, these are my molecular orbitals. Well, this is the ground state of hexatriene. In the excited state, 1 electron from the HOMO will jump up. If I give just the exact amount of energy for this gap, delta E. So one of these electrons are going to jump up in the excited state. The point is, the larger the conjugated system is, the closer the levels become. When they become closer, then the energy gap is smaller, and that's associated with longer wavelengths. So say the gap is, here's that equation. Oh, I had it somewhere else. If this becomes smaller, that lambda max become larger. So the more extended the conjugation is. And what we learned then from UV visual is that if we have or not a conjugated system. And when we look at the lambda max, we will know how extended, how large is that conjugated system. So that's the kind of information that we will get from UV visual. And that's the origin of colors. So we will have, for example, compounds just like lycopene has extended conjugation. That's what gives the tomatoes the red color. So it absorbs light in the green visual range, so we see the opposite, which is the red. And carotenes are orange, so they absorb light in the blue color range, and so on. But again, that's the kind of information we're learning about conjugation when we look at UV visual spectroscopy.